Well, hi there. Welcome to week 5. Can you believe it? Week 5. Last week, you started learning about exponential form of numbers and how exponents really are just a way of writing repeated multiplication. This is not the first time you've seen exponents, but it's probably the first time that you've started working with things and doing operations in exponential form. So let's do a quick review of the rules that you learned. Sharing, here we go. The rules that you learned last week and the vocab that you developed. So first of all, if you have an exponential expression, say x to the power of n. X is the base, n is the exponent, and you keep hearing this word power, and I just want to make sure you guys understand that all of it together, so this is the base, this is the exponent, and this whole thing is called a power. In fact, this is called a power of x. You name it by the base. This right here, the base would be 5, the exponent would be 2, but the whole thing is called a power, and more specifically, a power of 5. Okay? You also learned last week a couple of rules that you can do with these. Product of powers. If you take a power, say a power of x times another power of x, these are individual powers because they each have their own base and exponent. So this is a power of x times a power of x. The rule is you add the exponents. The base remains, but you add the exponents. You also learned about quotient of powers, and that is if you take a power and divide by a power, you can subtract the exponents. And that's all about how the patterns of repeated multiplication work. That's where these rules come from. But of course, once a mathematician figures out, hey, this always works, then we make a rule for it, and then we become more efficient. Now, let's learn more about exponents and how they work. So we have products of powers, we have quotients of powers, but actually there's a lot more you need to know about that. So to get ready, will you all please get out page 11 right now? Not page 11. We're well beyond page 11. Page 14. I was just looking at the wrong thing. Everybody get out page 14, get your pens, pencils ready, and be ready to write. Here we go. And here we go. Page 14. The top is, these are the instructions it says. Rewrite each number in exponential form with a base of 3. Okay, so I'm going to change each of these just regular old whole numbers that I recognize them as what they are. I'm going to change all of them to a power of 3. That's that math language there. Well, what if it just says 3? Remember, everything has an exponent. Even if it's not written, everything at least has an exponent of 1. So 3 is the same as 3 to the 1. 27 is equivalent to 3 to the 3rd, and you can type it in your calculator if you don't believe me. 81 is equivalent to 3 to the 4th. 3 times 3 is 9 times 3 is 27 times 3 is 81. And 3 to the 6th is equivalent to 729. Just once again reminding you that a lot of numbers can be written in a different form called exponential form. It's not actually a different mathematical value, but it is written in a different form. Okay, a couple more things we need to be familiar with about how exponents work. When you put things in exponential form, you can become a more efficient mathematician. Now, for example, right here, we are going to learn what happens is if I have a power of 3 not multiplied by a separate power of 3, but raised to this extra exponent, okay? It is called a power of a power. Powers of powers. We have a lot of alliteration with the letter P here. Product of powers, powers of powers. So what does this actually mean? If I expand it out, what I have is 3 to the 3rd twice. Exponents mean repeated multiplication. So that means, oh, I'm supposed to do 3 to the 3rd times 3 to the 3rd. Now I can expand this further, but you'll see we actually already have a rule for this. That means 3 times 3 times 3 times 3 times 3 times 3, which is of course 6 of them. Oh, okay. Yeah, well that makes sense. As soon as I split it up here, I changed it from a power of a power into a product of powers, and I can keep the base the same and add the exponents. All right, let's look at this one. This parenthesis here means all of that inside the parentheses, all those powers. This is a power of A and a power of B. And all of that is supposed to be raised to the fourth power, which means everything in the parentheses gets multiplied 1 time, 2 times, 3 times, 4 times. Oh, now I have a product of powers again. Now they each have their own bases with their own exponents. Therefore, this is a power of A times a power of A times a power of A times a power of A, and I can just go 2, 4, 6, 8. This would make 8, A to the 8th, and B to the 4th. Okay, let's look at one more. Does it matter if you put a fraction in it? Well, no, not really. This still means everything inside of the parenthesis raised to the third power. That means I need to multiply this. 1, 2, 3 times. And now, based on what I know about fractions, I'm going to multiply across the top. You multiply numerators. That's how multiplication with fractions works. It has since elementary. It's no different here. I just have to now apply exponent rules to it. In fact, I'm going to consider these all powers since I'm thinking that way. 2 to the 1, 2 to the 1, 2 to the 1 is actually 2 to the third. There's 3 of them. Yes, that is equivalent to 8, and I could evaluate that. That's what the word evaluate means, would be actually calculate that exponent. Just for the sake of seeing the patterns, I'm going to leave it exponential. X to the third, X to the third, X to the third equals X to the 9th. And then on the bottom, I have Y to the third. Now, the question is, what is happening from here all the way to here? Can we see the mathematical patterns that would allow us to perhaps skip the expansion step? In fact, right here, look at that one. This one already says, this one is too long to expand. Find the shortcut. And this is the point in class where I'd say, you guys, what's going on? What's the shortcut? How do I get from here to here? And you guys very quickly see, oh, what's happening here is, if I take a power and raise it to another power, I'm going to split that into 2. And really, I've taken this and turned it into the repeated addition, which repeated addition in the beginning is just multiplication. So the fact is this. Here I go. I'm going to come over here. And I'm going to write power of power. If I take a power, we'll say a power of x. So this is a power of x because the base is x, x to the n. And I raise it to another power, we'll call m. Notice this is not a power times a power, it's a power raised to another power. It's different because it doesn't have its own base. What I do is just multiply those exponents. And I'm going to write that little note down here. I'm going to put a little star here. I'm going to tell myself, multiply the exponents. That's the shortcut. If you see all this stuff being raised to this floating extra exponent up here, multiply the exponents. And you multiply all of the exponents. Make sure it's the exponents. Remember, this does have an exponent. 2 is not an exponent. 2 is a coefficient. It's a base. Never, ever multiply a base by an exponent. That's a very common mistake that students make. I want to make sure you guys don't make that mistake. Did you guys hear that? What's that thing that I said? Are you paying attention? Oh, never, ever multiply a base by an exponent. That doesn't make any mathematical sense. Don't do it. Never multiply a base by an exponent. Never multiply a coefficient by an exponent. Multiply exponents by other exponents. Okay, thanks for paying attention. So back to this. If I'm using a shortcut here, hopefully I didn't just freeze in a weird place. If I'm using a shortcut here, I'm going to multiply these exponents. So 2 times 5 makes this 3 to the 10. 10 times 5 is a to the 50th. And 5 times 11 is b to the 55. That would sure be a lot of 3's and a's and b's to write out. No need to expand it. Use what makes sense. Use your shortcuts. Okay, we're going to try a couple of examples here to make sure we understand this new idea. And of course, as you'll see, we bring this new idea of power into what we already know. So we use this in conjunction with product of powers and quotient of powers, and you have to be able to put all of these rules together. So let's try this out. Right here, I see a power of a power. I'm going to remind myself right now, you should do this too, that I am only going to multiply exponents. So sometimes we forget, this 2 is a base. Should I multiply an exponent by a base? No, never do that. That doesn't make any sense. So I'm going to write in here that these have their own exponents. They are there. We just still need to write them. That'd be redundant if we put the exponent of 1 on everything. But they are there. So I'm going to multiply these exponents. That makes this 2 to the 4th, x to the 4th, y to the 8th. I just used the power of a power rule. I multiplied the exponents. What did I just use? Power of a power. Now, I also have this still over here. That was not applied to the power of a power. And my numbers got bigger as I wrote that way. I don't know why. But that was not part of the power of a power, so nothing happened to it yet. Now something's going to happen to it because now I have 2 powers of 2 and I'm multiplying them. So I just did power of a power and now I'm going to do product of powers, which means I'm going to now not multiply the exponents. Now I'm going to add them because this is 4 of them and 6 more of them, which is 10 total because that's back to product of powers. And the rest of this, these are all different bases. So I just put them on my answer. Now, could I evaluate this part? Absolutely. I could type in my calculator 2 to the 10th and get the number and put that as the coefficient. Let's see what it is. 2 to the 10th. I could absolutely put 1024 on the front of this. It's equivalent. We're working on exponential form, so I'm fine leaving it that way. All right, let's try this again. Here we go. Power of a power. Okay. All of this gets raised to the power of 3. Once again, don't forget, you are multiplying exponents, and if you don't see an exponent there, it is a 1. It's there, but it is a 1. Okay, here I go. Across the top, multiplying exponents. So a to the 12th, b to the 6th, over b to the 3rd. Okay, I took care of power of a power. That's done. The parentheses are gone. I don't have any more floaty exponents, so I'm done multiplying. Well, I'm done with that shortcut. I'm done multiplying exponents. Now I'm going to do quotient of powers because that bar is a division. There's no other a's to combine this with, so that stays a to the 12th. Quotient of powers tells me to subtract exponents. 6 minus 3 is 3, and I have more on the top, so they stay on the top. Done. So, to add to your rules, you now have product of powers, you have quotient of powers, and you also have power of a power. Add exponents, subtract exponents, multiply exponents. Okay, we have one more really important thing we need to learn, and actually it's 2 more things, but it comes from the same patterns. So what I want you to do next for me on this page 14 is I want you to take a look at this table. In columns, I have listed powers of 5, and they're all called that because they have bases of 5. Then we have powers of 4, all with bases of 4. Powers of 3 with bases of 3, and powers of 2 with bases of 2. And I want you to evaluate these, and I want you to do it with a pencil, and I want you to do it without a calculator. Give your best guess as to what you think these answers are. Some of these you should absolutely know. Some of these you might be guessing. But you're going to pause me right now and see how much of this table you can fill in and do it with a pencil or, you know, be ready to cross off and write next to it. So pause me, see if you can fill in this table. Okay, I'm going to tell you right now that this in purple right here is usually the one part of the table that most of us get correct. Okay, those are positive exponents. We've worked with those since elementary. We understand they mean repeated multiplication. So those, if you don't have those quite correct, erase and fix it or cross it off and fix it, whatever you need to do. But most of us get this part correct. It's down here where our brain wants it to be one way. It really wants it to work a certain way, and it just doesn't work that way. Let me show you what I mean. Let's focus on the patterns here. Mathematics is all about patterns, and if you can figure out the pattern that's happening, then you can figure out why the rule is what it is. So notice these powers of 5. The pattern that's happening is that every time I move down a box, my exponent is just going down 1. So the exponents are moving down in the pattern. Let's see what happens to the evaluated answer as that exponent moves down, okay? From here to here, mathematically, as you move down one exponent in the power of 5, I'm moving down exponents, so I'm actually dividing, right? From here to here, I am dividing by 5. That's what's happening. And then that pattern continues here. I'm actually going to change that just to make sure we're connecting it. I hope you understand that dividing by 5 is really the same as timesing by 1/5. That's again an elementary concept that sometimes we forget about. It's called the multiplicative inverse. It's also just that division is the same as multiplying, but multiplying by the multiplicative inverse. Okay? That's why when you learn division with fractions, you learn silly tricks like copy dot flip and things like that. Okay, but it's all about dividing by 5 is really taking a fifth. So really what's happening as I move down a step, if I move the exponent down, my answer is now a fifth of what it was before. 125 times a fifth is 25. 25 times a fifth is 5. Mathematics needs to follow its own patterns. So I need that pattern to keep going. Tell me, what is 1/5 of 5? Or 5 divided by 5? Certainly not 0, you guys. I know that's what your brain wants it to be. You have to retrain your brain today to understand that this exponent notation means something different. If I wanted the answer to be 0, I simply would have said 5 times 0. That's not what I said. I said 5 to the power of 0. It looks different because it is different. It has a different meaning. Guess what 5 to the 0 is? 1/5 of 5 is 1. Okay, stick with me on this across here. Okay, watch this. New pattern because we have a new base. Now as I go down one exponent, I'm not taking a fifth anymore. I'm taking a fourth. And then as I go down, I take a fourth. I must continue this pattern. So if I take a fourth again, what is a fourth of 4? What is 4 to the 0? 1. What? That's super weird. Let's keep going. Your brain doesn't like to accept it at first. You got to force it to accept it. This has a new pattern because it has a new base. Of course, as we go down an exponent, we are now taking a third. We're taking a third. If I take a third of 3, guess what 3 to the 0 is? You guessed it, it's 1. And this pattern here, I am now taking a half. Every time I go down an exponent, I am taking a half. And guess what a half of 2 is? 1. And if you don't believe me, you can type it in. 5 to the 0 is 1. Guess what? 243 to the 0 is 1. This pattern will happen no matter what your base is. So what this means to me is that I am ready to write a new rule over here. Are you ready? I'm going to write anything. We'll call it x because it can represent anything. To the power of 0 always equals 1. Not 0. That's what your brain wants to say. When I ask you this question on future notes and future videos and I say, what's 5 to the 0? You're going to want to say 0. Stop it. Stop it from coming out. Don't let your mouth say it. 5 to the 0 is 1. Anything to the power of 0 is 1 because it's not timesing by 0. Why would we write it differently if it meant the same thing? It has a whole different notation because it has a whole different meaning. By the way, let me just prove to you really quickly one other reason why this is the case. Remember the quotient rule? It goes right along with it. If I had x to the 5th over x to the 5th, you know that's 1, right? Because in mathematics, anything divided by itself is 1. But if you follow the quotient rule and subtract those exponents, you get x to the 0. So it has to equal 1 because that's the only way all of this mathematics makes sense together. Okay, so that's first new thing down here. Really weird thing that our brain has to adjust to. Anything to the power of 0 equals 1 every single time. Now here's the other place that you might need to erase and cross things off. Again, I know what your brain wants this to be. You really want this to be -5. You really, really do. But I'm going to tell you this really important thing right now, okay? Negative exponents do not make negatives. Did you hear that? Did we all hear that? Negative exponents do not make negatives. They just don't, okay? If I wanted a negative, I would have just told you to times it by a negative. And that's not what I did. I told you to take a negative exponent. And you know what that means? We are still following our exponent patterns. And you know what that means? We are still following our take a fifth pattern. So if I have to keep following the pattern, and I do, if I take a fifth of 1 so that I can go down another exponent, what is a fifth of 1? Not a negative, but a fraction. 5 to the -1 is 1/5. And if I keep following that pattern, what is 5 to the -2? Well, a fifth of a fifth is 1/25. And if I go down one more exponent, I need to keep taking a fifth. That's the mathematical pattern here. What is a fifth of 1/25? 1/125. Whoa, what? Our brains don't like this at first, and that's normal and natural because it's a brand new notation. It's a brand new way to write numbers we already knew about, fractions. You can write fractions in exponential form. Now I want you to notice one more really important thing here. This isn't just any old fraction. This is the positive exponent flipped over. In math, we call that the reciprocal or the multiplicative inverse. A negative exponent makes a reciprocal. Look at this. 5 to the positive 2 is 25, and 5 to the -2 is 1/25. 5 to the positive 3 is 125, and 5 to the -3 is 1 over it. So we're going to write our rule over here, and then we're going to go finish this table. So now we also know there is such a thing as a negative exponent. Not only do we know about it, but now we know it doesn't make negatives. No, we're never going to put a negative on that. That's not what we want. We put 1 over the power because a negative exponent makes a reciprocal. Negative exponents are another way to show that we want a reciprocal. We want to flip it over. It's one more way to write that, which is really neat when you think about it. So 4 to the -1 is actually another way to write 1/4. It is the reciprocal of 4 to the positive 1. 4 to the -2 is the reciprocal of that, 1/16. And 4 to the -3 is the reciprocal of that, 1/64. 3 to the -1 is 1/3. 3 to the -2 is 1/9. And 3 to the -3 is 1/27. 2 to the -1 is 1/2. 2 to the -2 is 1/4. 2 to the -3 is 1/8. Negative exponents make fractions. They make fractions. And the cool thing is if you have a fraction, you can actually turn it back into a negative exponent and work with exponent rules instead of fractions. That's super handy for some of us that don't like working with fractions, which is not me, of course. I love fractions, but I also love exponents and probably love exponents more. So I'm going to take you through now some examples that kind of put all of this together. I want you to listen and I want you to write, and then I want you to trust that we're going to take you through lots of practice this week, and your math teacher is going to be here to help you put all these rules together and make sure we're keeping them all straight. So right now, listen, watch, write, and try to process what's going on. Do you know what I see right here? I see zeros and I see negatives, and I kind of get freaked out because I have these new rules. Don't freak out. I actually see a product of powers. I see that all of these have a base of 8. And what that means is I can just add all their exponents. So I'm going to do that. I'm going to follow my integer rules from 7th grade. 0 plus -3 is -3. -3 plus 5 is 2. Wow, I simplified it. All done. The base stayed the same. Could I evaluate it? Absolutely. Okay, so this is simplified exponential form. This is evaluated. Found the answer. Cool, that was easy. Let's try another one. I'm going to change colors just for fun. These all have bases of 5. So I'm going to do that again. I'm going to add the exponents. Here we go. 5 plus -4 is negative, what? Not 5, that's a 3. 3 plus -4 is -1. -1 plus -1 is -2. Now, people are tempted right there to box that answer and call it good. I'm going to tell you one of those mathematical conventions that Math Antics guy talked about a while back in that video is that we don't leave negative exponents in the answer. We use them in our calculations to help us manipulate things, but we do not leave negatives in our answer. So I need to show that I understand this is a reciprocal. I flip it down there. And again, I can leave it like that in exponential form, or I can actually evaluate it. 1/5² or 1/25. The negative exponent makes a fraction. Stick with me, here we go. I'm gonna do these parentheses first, because that's what PEMDAS has taught me for years and years. 5 minus 2 is 3 to the 5th times 3 to the -8 plus 5 to the 0. Well, that's a 1. I'm just gonna change that right now. Those are now a product of powers. 3 to the 5th, okay, I'm gonna add those exponents. That is 3 to the -3 plus 1. And now, this one's a little weird, that is a fraction. 1/3 to the 3rd, which we know this one, it's 1/27. I can evaluate it or leave it in exponential form, plus 1. Whoa, I could just make that a mixed number then, right? 1 and 1/27. Woo. There we go. We put together a lot of exponent rules in there. Okay, I'm gonna keep going. Stay with me. Parentheses first. 3 plus 1 is 4. That's 4 to the 6th. 7 minus 3 is 4. That's 4 squared. Hey, this is a quotient of powers. I'm going to subtract those exponents because those bases are the same. I'm not going to do anything with the bases. I'm going to work with the exponents. 6 minus 2 is 4. 4 to the 4th. Could I evaluate it? Sure. I think it's 256. I'm sure you guys will email me and message me if I'm wrong about that, but I think it's 256. All right, number 11. Watch this. You ready? I'm going to say all the great math rules I'm using and show it at the same time. Power of a power, multiply the exponents. Power of a power, multiply the exponents. Parentheses, subtract. Ooh, I'm gonna get really tricky right here. You guys ready for me to get really tricky right here? Right now those bases aren't the same. I'm gonna make them the same. You ready for this? 4 is 2 squared. Oh my goodness, I just turned that into another power of a power, because I'm pretty brilliant like that. And now this is 2 to the 6th times, look at this, power of a power, multiply exponents, product of powers, add the exponents, 2 to the 0, what? That whole thing simplified to 1. That is bonkers. All right, last one. And I promise we're gonna slow it down and practice all of these, so no need to panic, just keep listening, just keep writing. I am going to remember that that's x to the 1. And I'm going to remember that that's just a coefficient. So whatever happens, that's probably just going to stay on the front. I'm going to write it on the front. And then I'm going to go power of x, power of x, power of x. Product of powers, add the exponents. I'll say that again. Product of powers, add the exponents. 5 plus -10 is -5 plus 1 is -4. Negative exponents are reciprocals. But this guy right here does not have a negative exponent. Watch this. You ready? That means the 2 stays on top and the x to the 4th flips to the bottom. Done. Whew, that was a lot. We're gonna practice it a lot over the next couple of days. Please let me know if you have any questions as you work. You got this. Exponent rule.